Hello everyone, this is Balu. Welcome to my channel Steel Cave. In this video, I am going to continue the second part of the design of lug plate. I have already discussed regarding the first part of lug plate, like what is the concept behind design of lug plate. If you have not yet watched that video, please go through that video so that you can understand what is the concept behind the design of lug plate. This is a calculation regarding the design of lug plate. In this problem, if you see here, I have considered some side problem which is a design of lifting lug plate. We have to design 4 number of lug plates, like each and every lug plate is carrying the same load anyway, and the 13.5 metric ton container is there in the site, and you have to lift that container from one place and you have to place at another location. For that you have to design a lug plate which is welded to that container block. Okay, now let's just quickly get into the video. Here you can see this is the container block. Okay, and this container block is attached to the lug plate through the belt, and after that chains are available, and similarly from chains it is transferring through the sling. Then after that hook is there here, and this hook is connected to the crane. So we have to design the lug plate to carry this container block so that the crane will place this container block from one place to another. Here you can see this is the elevation of the container block. The lug plate is welded here. Clearly these lug plates are welded to the container block, and this is the plan of the container block. This red color indicates the lug plates and it is attached to the whatever the chains, and this black color indicates the chains. So these lug plates are inclined in this direction. Okay, I am just considering a example problem. What is the job we have to do? We have to lift that container block through the crane and we have to place it in the other location. Here the whatever the given data is, the weight of the container is 13.5 metric tons and load acting on each lug plate. Here there are 4 number of lug plates which are welded at 4 corners of the container block. So each and every lug plate will carry 13.5 divided by 4, that is 3.37 metric tons each. Now let us factor this load coming onto the lug plate. Factored load acting on each lug plate is 1.5 times the 3.37 metric tons, which is equal to 5.07 metric tons, which is almost near to 5 metric tons. So I am considering the 5 metric tons. Okay. Next, coming to the D-shackle. So this lug plate is connected to the D-shackle, and these D-shackles are available in the market and of each rated capacity. So here we require 5 metric ton capacity D-shackle. So I am considering the D-shackle of 5 metric tons capacity having pin dia of 32 mm. Here you can see this is the details of the D-shackle, and this D-shackle is having 32 mm and grade of 40 I am considering. So better you can watch this snip so that you can better understand the details of the D-shackles which are available in the market. Now coming to the thickness of the lug plate. So this is a trial and error basis. First of all, we are considering certain thickness of the lug plate and we are going to check that thickness. If the checks are getting passed, then we are going to give that thickness of the lug plate to the site. If it is not passing, then we have to increase the thickness, and similarly the trial and error continues. So initially I am considering 10 mm thickness plate, and it is as per 1730 1989 codes. Now whatever the lug plate we are going to consider, to place that D-shackle pin in the lug plate, we have to calculate the diameter of the hole. So as per table 19, see here, this is the snip of the table 19 from the IS 800 2007. So whatever the design I am going to do, it is as per IS 800 2007 code only. I am not considering any foreign codes, and the procedure, whatever the formula is going to change, but whatever the concept behind the design of lug plate is almost constant in each and every code. So let us calculate the diameter of the hole. See, D naught is equal to D plus 3 mm from the table, which is greater than or equal to 24 mm dia of the bolt or pin. The 3 mm extra we are going to provide, that is D plus 3 mm, that is 32 plus 3 mm will give the 35 mm. 32 mm is the dia of the pin regarding the D-shackle. So next we have to calculate the minimum edge distance, which is as per clause 10.2.4.2 as per IS 800 2007, and you can see the snip of the IS 800 2007 clause 10.2.4.2, which is given as 1.5 d naught edge distance. The 1.5 d naught is nothing but 1.5 times diameter of the hole, that is 35 mm. You will get 52.5 mm. This is a minimum edge distance. So I am providing 75 mm for the, like for safety side I am taking 75 mm. See, let us understand what is this edge distance. For example, this is a lug plate and this is a hole. This edge distance is nothing but the distance between the center of the hole to the extreme fiber of the lug plate. This is nothing but the edge distance. Anyway, you know the diameter of hole is nothing but this is the diameter of the hole. Here lug plate is welded to the container. Now let us get into the checks for a lug plate. That is, first check is nothing but check for shear. As per clause 8.4.1 as per IS 800 2007 code, the design shear strength of the bolt is nothing but Fu by root 3 gamma mb into whatever the Nn Anb plus Ns Asb. The snip you are going to see, it is clearly visible, okay, but whatever the Nn into Anb, it is regarding the bolt. But here I am going to consider the net area. See, there is also we have to consider the area which is resisting the shear, but it is regarding bolt. But coming to the plate, just we have to consider whatever the net area which is resisting the shear. See, we all know like how the failure pattern or failure plane propagates. Whenever the P load is acting on the lug plate, in the 45 degrees angle, the failure propagation will take place. This is already I explained in the previous video, so please go through that video so that you can understand clearly regarding the concept of design of lug plate. So here this is the two planes which are resisting the failure regarding shear, but for safer side I am considering only single plane. For example, I am considering only this single plane. The net area whatever resisting that shear, let us calculate. That net area is nothing but, for example, this plane I am taking. If you see that plane, this is a thickness and this is nothing but distance from E minus d naught by 2. See, for example, this is the center of the hole, this is the edge distance, you all know, just now I explained, this is the edge distance. Next, coming to this distance we have to measure. This is nothing but E minus d naught by 2. And whatever the thickness which is into the plane, okay, hope you understand, the thickness is into the plane and E minus d naught by 2 is this distance, and that is the net area which is going to resist the shear. If you multiply this T into E minus d naught by 2, you will get the area which is resisting the shear. That is only I am doing here. That is thickness into edge distance minus diameter of the hole by 2. So you all know thickness is 10 mm I considered. It's 75 minus 35 by 2. You will get 575 mm square as the net area. Now let us calculate the design shear strength of the lug plate. Here I am considering the grade of steel as 410 Newton per mm square and 575 mm square as the net area. Root 3 into 0.125, which is already given in the formula. That is gamma mb is a partial safety factor, that is 1.25 from the code, and I am dividing it with 10 to the power 4 so that I can get the value in the metric tons directly. The whatever the value, this is nothing but in newtons. If I divide it with 10 to the power 4, I will get it in the metric tons. So I am getting 10.88 metric tons, which is greater than 5 metric tons, hence the plate is safe in the shear. Coming to the bearing, this is also the design bearing strength. This is also given in the IS 800 2007 code. Here you can find the snip of the IS 800 2007 code regarding the design bearing strength of the bolt. I am just using the whatever the formulas we are going to use for the bolt, that is the same formulas I am using here in the plate, but the difference is whatever the net area they are going to consider in the bolt and coming to the plate is different. So let us design for the design bearing strength. The formula I am taking here is like Fu by gamma mb into 2.5 kb into dt Fu is the actual formula, but I am considering whatever the dt is nothing but the net area which is going to resist the bearing. In case of bolt, it is diameter into thickness, but here the net area will going to change. So let us consider it as AN, and similarly remaining thing is same, you all know. Next, KB is the factor which is nothing but minimum of E by 3D naught minus P by 3D naught minus 0.25 FUB by FU and 1. And this whatever the pitch is not there in case of this lug plate, so I am directly taking it as 0, it is not considered, and E by 3D naught I am going to consider. In case of lug plate, it is FUB is nothing but pin grade, but in case of bolt we are considering bolt, so here you have to consider this pin grade, and Fu is nothing but grade of the pitch, and 1 you know. So anyway we are considering that pin grade and plate grade is same. Like for example I am taking, if you are doing a real time problem of pin grade is different and also plate grade is different, please consider this factor also. Here I am not considering this factor. Next, E by 3D naught means nothing but 75 is the edge distance, 3 into D naught is nothing but the diameter of the hole, 35 mm, and minimum of 0.7 comma 1, that is nothing but 0.7. Substituting the formula, that is 410 by 1.25 partial safety factor, 2.5 into kb we have already calculated, that is 0.7. N is the net area. Here what is the net area you have to consider, this is the important point. Whatever the formulas you are going to use and what are the calculation you are doing, that is all okay, temporary, but the important thing is the net area calculation. If you understand the calculation process of net area, then you are strong in your fundamentals and also concepts. So here you can see this pin is touching the lug plate at this location. So whatever the fibers regarding this lug plate is going to bear here near the higher stress concentration. So whatever the net area you have to consider is this plane area. So if you consider the projection of this plane area, this is a load acting, for example P, projection area. This length is nothing but the circumference of the contact of the pin and also plane. Circumference is nothing but pi d by 2. This diameter of the hole is nothing but d naught. So pi d naught by 2 is the half of the circumference of the lug plate, and whatever the projection into the lug plate is nothing but thickness. So pi d naught by 2, and this is the thickness. This is the projection I am considering. So pi d naught by 2 into T is the net area resisting the bearing. Here pi d naught by 2, 35 you all know, that is the diameter of the hole. To calculate the pi d naught by 2 into thickness, you will get the 550 mm square as the area resisting the bearing. Now let us calculate the bearing strength. That is already you know the formula. Just substitute in the bearing strength formula and you will get 31.5 metric tons, which is greater than 5 metric tons. So hence the lug plate is safe in the bearing. Now let us get into the final thing, that is check for tension. So you can observe the snip of the check for tension, that is as per 6.3.1 clause. The tension formula is given in the IS 800 2007. This is the snip. Next, coming to the design tension strength, 0.9 ANFU by gamma ml. So you all know that important thing is whatever the net area calculation is very important. So here the whatever the plate here, the rupture is going to take place in this manner. So we have to calculate the net area of this resisting section. So I am considering one section, for example. If you take the projection, which is similarly E minus D naught by 2, which you already know, I have calculated in the initial stage for check for shear only. This E minus D naught by D is the distance. Next, coming to the other thing is thickness. See, for example, this is the center of the hole. This is the edge distance. This is the half of the diameter of the hole, D naught by 2. So if you deduct E minus D naught by 2, you will get whatever the distance this one. So I am taking that as E minus D naught by 2. So net area here you can see T into E minus D naught by 2. Here there are two planes which are resisting for the tension. So into 2 I am doing, and similarly we will get the net area calculated is 1150 mm square. So let us substitute in the tensile strength of the plate 0.9 into An into Fu by gamma ml into, I am dividing with the 10 to the power 4, so that we can get the value in the metric tons, which is greater than 5 metric tons. So hence it is the safe in the tension. Let us consider some miscellaneous checks. For example, if you are building that lug plate to the container, then you have to check this weld strength so that it should resist that load coming onto the weld. This is the one thing, that is you have to check the weld strength. Here we are assuming that the load is passing exactly through the axis of the lug plate. For example, any problem is occurred in the site, and suddenly that sling is acting in the inclined direction with an angle of theta. Accidentally it will happen, so that this whatever the load coming onto the lug plate will get into components or divided into components, and for example P sin theta, this is P cos theta. You have designed this lug plate for this axial load, but the load is coming in this direction, that is P sin theta and P cos theta, for example. Okay, then what will happen means, whenever the load is passing exactly through the axis, this is the major axis of the lug plate. So this is nothing but B, and this is nothing but D. So let us consider the lug plate. That is, for example, this is the lug plate in the plan. The load is acting axially across the lug plate P, and this is the major axis of the lug plate, and this is nothing but B, and this is nothing but D. So whatever the section modulus is nothing but D into D square by 6. Here D is very much greater than B. So here square term is there. Anyway, section modulus is very high in the major axis. Whenever the load is, like I have considered, I said, that is, it is divided into components, and for example, accidentally it is coming into the through the minor axis, that is P sin theta, for example. When we consider this P sin theta, the load is acting through the minor axis. So in this case, whatever the Z, this is major axis MJ, Mn minor axis, D into D square by 6 is the section modulus of the lug plate through minor axis. That time, you know, D is very much greater than B. Whatever the bending stress, you know, sigma is equal to M by Z. The Z is very less. So bending stress, which is coming in through the minor axis, very high compared to the major axis. So this is the thing we have to keep in the mind. So whenever you are going to design this lug plate, please keep in mind, for the accidental loads, load action will change abruptly. So what we have to do? We have to place the stiffeners. For example, if we place the stiffeners, then whenever the load coming onto the lug plate is divided into components, for example P sin theta, these are the stiffeners. In the minor axis also, this resisting area or the section modulus will going to increase in case of minor axis. Okay, this is just a rough explanation regarding the whatever the bending and also check for the weld. These are the miscellaneous checks you have to do. Okay, if you want like any design problem regarding this whatever the bending and also welding check, please comment in the comment section so that I can do the further videos also. Please hit the like button and also click on the subscribe button so that you can never miss the updates regarding my channel. Okay, thank you for watching this video. See you in the next video. Thank you.